Hello everyone, welcome to the final lecture of this term. Last week, we talked about correlation and regression, which are used to assess the relationship between two numerical variables. For this week, we're going to expand on the topic of the assumptions of the hypothesis test. At the end, I'll do some review of the class and go over all the tests we learned in this class. Now, let's start with the test assumptions. We learned 5 major types of hypothesis tests in this class. All of these tests have to meet certain assumptions for their test results to be valid and robust. Here, I summarize 3 common assumptions across the tests we covered in this class. The first one is that the test has to be based on data from a random sample, meaning that each subject in the population has equal and independent chance of being selected in the sample. This assumption is the most common one which applied to almost all the tests we learned in this class. The second assumption is unequal variances. This assumption applies to t-test and ANOVA. In t-test, it means the two groups should have this, equal variances, while in ANOVA, all groups must have equal variances. The third common assumption is about normal distribution. This one applies to tests where at least one numerical variable is involved, such as t-test, ANOVA, correlation, and regression. It means the measured value of a numerical variable should follow a normal distribution. What I want to bring to your attention here is the assumptions for equal variances and normal distribution are both referred to the feature of the population, because the population is what we are most interested in. In the real world, usually we're not able to measure everyone in the population, so we'll need to take a representative sample from which we may get an idea on the population. Now let's talk about the assumption on the random samples. First, please recall what we learned in lecture 1 on the content of the randomness and random sample. As a random sample, it means everybody in the population has equal and independent chances of being selected. Equal means the chances of being selected is the same for each subject in the population. For example, if there are 4 people in the population and we want to take a random sample, each subject has 25% chances of being selected. Independent means the selection of a subject is not influenced by the selection of another subject or other subjects. Now let's look at an example. In the case here, the researchers wishes to study the mental health issues of college students. You can pause to read the text here. Now you've read the details on the example. Please think about these questions. What is the population? What is the sample? And finally, is this a random sample? Here, in this case, the population are the 40,000 students enrolled in the Midwestern Public University. The sample are the 939 students who completed at least 75% of the survey. How did they end up with these 900 students? First, they randomly selected 5,000 email addresses from all the enrolled students from the university registrar system and sent them the invite to participate in the survey. Then, among these 5,000 students who got the invitation, 1,056 of them began the survey. The students who didn't complete at least 75% of the survey were then removed from the sample, which gave them the final sample of 939 students. So, is the assumption of random sampling met in this case? You can pause here and think about it, then press continue when you're done. In this example, all the samples are collected randomly based on their university email addresses. although the relatively low participating rates may compromise the randomness of the sampling. Here, we can still say the assumption of random sampling is met. Now let's look at another case. This is an intervention study, and they want to study whether reducing sitting time at workplace will improve workers' health. You can pause here and read the details. When you're done, press continue. Again, according to what you just read, please think about these questions. What is the population? What is the sample? And is this a random sample? You can also pause here and press continue when you have your answers. In this case, the population are the employees of the Health Promotion Department and Health Partners, which is a nonprofit member-governed health system in Minnesota. The collected sample are the 34 employees who signed up to participate in the project. What about the third question? Is this random? From the text, we can see the participation is totally voluntary, and the subjects in the sample was not randomly selected. So clearly, in this case, the assumption of random sampling is not met. So what we can do when the assumptions of randomness is violated? First, we need to know that in practice, it is extremely rare to have a perfect random sample. Even all the subjects are selected using random sampling, low participating rates, high loss to follow-up, and other factors may all compromise the randomness of the sample. Like the first example we just read, although 5,000 students were randomly selected through the university email system, the researchers ended up with a final study sample of less than 1,000 students. It is quite possible that students who are more concerned about mental health may decide to participate and complete the survey. These students may have mental health status which is better or worse than the general student population. Second, in the real world, a perfect random sampling is sometimes hard to conduct, especially for large-size population. In these situations, some complex sampling methods are usually used, such as stratified, clustered, or multi-stage sampling. Now, please recall the sampling method of the Canadian Community Health Survey, which we used for our assignment. It uses a very complex multi-stage sampling method to get the representative sample of the Canadian population. Usually, we'll need to use some analysis tools to account for this complex sampling method, like weighting or bootstrap method. But in our assignment, to simplify the issue, we assume it is a random sample we took. Generally speaking, if the sampling method is non-deterministic or its impact is small, we can proceed with parametric tests. All the hypothesis tests we learn in this class by far are all parametric tests. I'll give more details when we move to the assumption of normal distribution later. Some issues may arise when we use parametric statistics with non-random sample. But I won't get into details here. The content is covered in another class. Now let's take a closer look at the assumption of equivariances. Both ANOVA and t-test assume that the variances are equal across all groups. This is an area with discussion and controversy, so we may not have a conclusive instruction to follow here. For now, within the scope of this class, you can use this rule of thumb. If the largest standard deviation is no more than 2 times of the smallest standard deviation, we can say the assumption of equivariances is met. Or we can say the largest variance cannot be larger then 4 times of the smallest variance. So what we can do if the assumption of equal variance is not met? As we already learned in this class, for the student's t-test, we have a very easy alternative, the Welch's test, which doesn't assume equal variance. In practice, since both ANOVA and t-test are pretty robust hypothesis test methods, even this equal variance assumption is violated, we can still make conclusions from the test results with confidence, especially when the sample sizes are equal and large. In this case, even a 10-fold difference in variance is somehow okay. But we do need to keep in mind that violating the assumption of equal variance will tend to decrease the power of the test. Here, I included a possible solution to use Welch's t-test instead of ANOVA when the assumption of equal variances is violated. I'm not going to go into details here. You're welcome to click on the link below if you're interested. Another solution is to use non-parametric methods, but I'll come back to this topic in the next few slides. Now we can talk about the assumption of normal distribution. There are different approaches which can help us determine whether the population follows a normal distribution or not. Some of them we already covered in this class. First, we can go to literatures and previous studies. If previous studies already found that the distribution of certain parameters follow normal distribution in their study population, when we have the same or similar population, we'll know it may follow the same normal distribution pattern in our population. The second method is to use histogram, which we already learned in this class. If the distribution shows a symmetric bell curve, we can say it's a normal distribution. Another plot, which is pretty helpful, is the quantile plot. Some people also call it a quantile plot or QQ plot. It shows the distribution of the data against the expected normal distribution. So we are able to determine if the data follows a normal distribution. And finally, we can use the Shapiro-Wilk test to determine if a distribution is normal or not. First, let's look at an example of biomass ratio distribution shown in this histogram. We can see in this case, the distribution is not symmetric and highly right-skewed. So this is not a normal distribution. Now, let's plot the same data into a QQ plot and see how it looks. Here, the x-axis shows the actual value of the variable, which is the biomass ratio here. The y-axis shows the value of an expected normal distribution. We already know that the data is not normally distributed. What the QQ plot shows here is the dots forms a curve. So we can see a curve here. Here, I show the QQ plot for another data which has a normal distribution. In this QQ plot, we can see all the dots approximately forms a straight line. So you can see it's like a straight line here. Therefore, in the QQ plot, when we see the dots somehow forms a straight line, we can say the data follows a normal distribution. The Shapiro-Wilk test is another method we can use to determine normal distribution. It is like a statistical test with its own non-hypothesis. You can perform this test using any statistical software, like JAMP. But be careful. The null hypothesis for this test is the data are normally distributed. Therefore, if you fail to reject the null hypothesis test, it means the data are normally distributed. On the other hand, if the null hypothesis is rejected, then the data is not normally distributed. Now we know how to determine normal distribution. What can we do if the assumption is violated? In the real world, if we have a real large sample size, the parametric test somehow will work fine. We can also do some transformations on the original data and run the parametric test based on the transformed data. Finally, we still have the option to use non-parametric tests for our data analysis. We know the means of large samples are normally distributed, so the parametric test on large samples will work relatively fine, even for the data that is not normally distributed. A rule of thumb we can refer to is if the sample size is larger than 50, we can treat distribution as normal. Another option we have when the normal distribution assumption is not met is to do data transformation. To do so, we need to make sure that the transformation changes each data point by some mathematical formula. In other words, we have to apply the formula to each data point in our dataset. Now let's look at an example. Here, this graph shows the distribution of measured mercury concentration. We can see it is not a normal distribution. The data is right skewed. We already know the transformation must be applied to each measurement in the dataset using mathematical function. So what function we should use? In public and occupation or environmental health studies, the most common type of transformation is the log transformation. It takes the natural log of each data point. Now back to our example. We have the original mercury concentration listed here, and we take the natural log of each measurement here. Then it gives us the value of each data point after transformation. To show this transformation in histogram, the graph on the left shows the distribution before the transformation. After we do the log transformation, the distribution becomes what's shown on the right, on the histogram on the right. So it goes from a right skewed distribution to a normal distribution. And here, y prime represents a transformed variable. Now back to the biomass ratio example we used in previous slides. The histogram on the top shows the right skewed distribution of the original data. After we do the log transformation, the distribution becomes approximately a normal distribution, which is the histogram at the bottom. Here is another example showing a right skewed distribution in the original dataset. Now let's do the log transformation. After the transformation, it shows an approximate normal distribution. To sum up, for the 4 scenarios below, you're probably going to need to use log transformation. First, the variables are likely to be the result of multiplication of various components. And second, It is the exposure data from environmental or occupational studies. Third, the distribution of the data is right-skewed. And fourth, the variance seems to increase as the mean gets larger. Something to keep in mind, if you do the log transformation on the data and run some analysis based on the log transformed data, you'll need to consider how to present and interpret the descriptive stats. Basically, when you interpret the descriptive stats, you'll need to reverse the transformation and use the geometric mean or geometric standard deviation to describe the data. Here, I list some other transformation and their transformation formula, such as r sine, square root, and etc. So you will have different options to choose for the data transformation. Now we know there are different kinds of transformation to do. How do we choose the correct one to use? First, we need to make sure the transformation is applied to each individual data points in the same way. And second, remember the purpose of the transformation is to make sure our data fits the normal distribution assumption. Therefore, we can try different transformation until we find the one which makes the data fits the normal distribution assumption. However, we cannot keep trying different transformation until we find a p-value which is less than 0.05 or the significant level for the main analysis. No matter what transformation you do, a valid transformation requires the same transformation to be applied to each data point, as I mentioned many times in previous slides, meaning it has one-to-one correspondence to original values. A valid transformation also shows a monotonic relationship with original values, meaning larger value in the original data will stay larger after the transformation. Using non-parametric methods is another option we have when the normal distribution assumption is not met. The non-parametric methods assume less about the underlying distribution, so they're also called the distribution-free methods. On the contrary, the hypothesis tests we have learned in this class are all parametric methods. They are called parametric methods because they assume certain distribution on a parameter. In most of the cases, they assume normal distribution. Most of the hypothesis tests we learned in this class have non-parametric equivalents, which are listed in the table below. Many of these non-parametric tests use ranks of the data to do the comparison. For the scope of this class, you don't have to know all the details of the non-parametric test. You just need to know they can be used as a backup plan when the assumption of the parametric tests are not met. That concludes all the content of this class. I'll do some review of the class from here. Now let's start. In biostats, a variable is any characteristics, number, or quantity which can be measured or counted. There are two types of variables. One is categorical variable, the other one is numerical variable. A categorical variable can be nominal, meaning there is no intrinsic order of the categories. For example, all the cities in the GTA area. When the categories show some kind of order, it is an ordinal categorical variable. An example is education level, which may start from elementary school education all the way up to graduate degree. A numerical variable can be continuous. For example, the concentration of silica dust in the air. It can also be discrete, such as number of injuries happened in a week. we use different statistics to describe the two types of variables. For categorical variable, we can use counts and percentage to show how subjects are distributed among different categories. We can also show this distribution using bar graphs, pie charts, and etc. For a numerical variable, we always use mean, median, and mode to describe the central tendency of the data, and we always use standard deviation or variance to measure the variation and dispersion of the data. To show the distribution in the graph, we can use histogram or the box plot. We also learned the z-score method in this class. It is designed to compare a measurement from an individual to a population distribution of measurements. We covered 5 different types of hypothesis tests in this class, including chi-square test, t-test, ANOVA, correlation, and regression. With the hypothesis test, we can assess the association between two variables. Depending on the types of the two variables, we are able to choose the most suitable hypothesis test to use. The chi-square test is used for the scenario where we want to examine the relationship between two categorical variables. Besides the chi-square test, we can also use contingency table or the mosaic graph to explore the relationship between two categorical variables. We covered 3 types of t-test in this class. The one-sample t-test, which is used to compare the mean of a continuous variable to a certain value. The paired t-test, which is designed to check if there is a change between two measurements taken on the same person. And last, the two-sample t-test, which can be used to compare the means between two groups. It is also the scenario where you have a numerical response variable and a categorical explanatory variable with only 2 levels. However, if you have a numerical response variable and a categorical explanatory variable with more than 2 categories, you should use ANOVA, the analysis of variance. It compares the means among more than 2 groups. Finally, if we want to study the relationship between 2 numerical variables, the tests we can use are correlation or regression. To explore the relationship between 2 numerical variables in a graph, we can use the scatter plot. In previous slides, I summarized all the tests we learned in this class. Each test is designed to be used in a specific scenario, mainly based on the types of the 2 variables involved. This will be the most basic and important skill you need to acquire from this class. So, when you are given a specific scenario, how do you determine what test to use? To simplify it, you can follow the 4 steps here, or ask yourself 4 questions here. First, which one is the explanatory variable or the independent variable? Second, which one is the response variable or the dependent variable? Third, what types of variables are they? And finally, based on the types of the 2 variables involved, what type of hypothesis test can be used? Now let's follow the 4 steps here and determine the test to use in some scenarios here. You can pause and read the scenario 1 here. When you finish reading, press continue. In this case, they want to study the effect of lead on children's health. So they measure the lead concentration in household water in parts per million, and children's IQ measured in points. The two variables involved here are lead concentration and children's IQ. You can pause here and think about what is the explanatory variable and what is the response variable. You can press continue when you have your answer. So in this case, the explanatory variable is the lead concentration in household water, and the response variable is the IQ of the children. Now we have known lead concentration is the explanatory variable and IQ is the response variable. So what types of variables are they? You can pause here. I'll give you the answer in the next slide. Okay, so in this case, the lead concentration is a numerical variable, and the IQ of the children is also a numerical variable. We know there are two numerical variables are involved in this case. What analysis we should use here to study the relationship between the two? You can also think about the null hypothesis for your study. You can pause and press continue when you have your answer. Because we have two numerical variables in this case, we can use correlation or regression to examine the relationship between the two. If we use correlation, our null hypothesis is rho, or the correlation coefficient, equals to 0. If we use regression, our null hypothesis is beta, or the slope is 0. Now let's look at scenario 2. You can pause here to read the details. Press continue playing when you finish reading. In this case, the researchers want to know if the skin pigmentation will influence the level of vitamin D. They measure the level of vitamin D in people with light, medium, and dark skin pigmentation. Again, please ask the 4 questions in your mind. Let's start with these two. What is the explanatory variable and what is the response variable? You can pause here and press continue when you have your answer. In this case, the explanatory variable is the skin pigmentation type, which is light, medium, and dark. And the response variable is the level of vitamin D measured in human body. Now, let's determine the type of variable for our explanatory variable, the pigmentation. You can pause here. After you choose your answer, press continue. The skin pigmentation is an ordinal categorical variable. There are 3 groups, light, medium, and dark skin pigmentation groups, which shows a skin color order from light to dark. Next, let's determine the type of variable for the vitamin D level. You can pause here and choose your answer. The correct answer is C. The vitamin D level is continuous numerical variable because the level of vitamin D in human body can be any numerical value. Now we know our response variable is numeric and our explanatory variable is categorical with 3 different categories. Let's decide the test to use. You can pause here and pick your answer. Press continue when you're done. The correct answer is D, ANOVA. When we have a numerical response variable and a categorical explanatory variable with more than 2 levels, we should use ANOVA. Now let's move to scenario 3. You can pause and read the details here. When you're done, press continue. In this study, they want to know whether men or women are safer drivers. So they took a random sample of the Canadian drivers. In their sample, 238 drivers died in the vehicle crashes. The rest 418 drivers didn't have any records of vehicle crashes. Here shows a contingency table summarizing the data of the study. Among the 238 drivers who died in the vehicle crashes, 167 of them were male drivers and 62 were female drivers. Among the 418 drivers without any crash records, 229 of them were male and 189 drivers are female. First, please find out the explanatory variable and the response variable in this case. You can pause here and press continue after you have your answer. So in this case, the explanatory variable is the sex of the driver, and the response variable is whether the driver died in the single vehicle crashes. Now please think about what type of variables are these two. You can pause here and press continue after you have your answer. Both two variables in this case are categorical. For the explanatory variable, it is whether the driver is male or female. For the response variable, it is whether the driver died in the vehicle crashes or they had no records of crashes. Now we've known that both two variables involved in this case are categorical. Which test we should use here? You can pause. When you have your answer, press continue. The correct answer is A. When we want to study the relationship between two categorical variables, the test we should use is chi-square test. Now let's look at scenario 4. You can pause here to read the details. Meanwhile, please think about what type of test we should use here. In this case, only one variable is involved, which is the score of the calculus exam. What we want to do here is to compare one measurement from a person to the population distribution of measurements. According to what we just reviewed in previous slides, we can use the z-score method. Using the z-score method, we will be able to calculate what proportion of students in the class had a score higher or lower than 58%, which shows how well the sister did compared to the rest of her class. Now let's go to the final scenario. You can pause and read the details here. Press continue when you're done. In this case, they want to know the total study time between full-time and part-time students. They took a random sample of the Ryerson students in the class, and they asked the students to report their total time spent per week studying for the class. The students also reported their status, whether full-time or part-time. In this case, there are two variables involved. Which of them is explanatory variable and which of them is response variable? You can pause here. When you have your answer, press continue. In this case, the explanatory variable is the full-time or part-time status of the students, and the response variable is the time spent per week on study for the class. Now, please think about what type of variables are the two. You can pause and press continue when you have your answer. So in this case, the full-time or part-time status is a categorical variable with two categories, and the response variable, time spent per week on study, is a numerical variable. Now we've known the type of variables involved in this case, what test we should use here. You can pause and press continue when you have your answer. The correct answer is B. When we have a numerical response variable and a categorical explanatory variable with only two levels, we should use the two-sample t-test. We have gone through some examples in previous slides. Now let's do a final summary of all the tests and the scenarios they may apply to. The summary table here shows the scenario where two variables are involved, where one is the explanatory variable and the other is the response variable. Both the explanatory variable and the response variable can be categorical and numerical. According to the different scenarios here, please fill in the blanks using what we learned in this class. You don't have to worry about the gray area in the table because it's beyond the scope of this class. In the three scenarios below, so these three scenarios below, only one variable is involved, and please fill in the blanks based on what we covered in this class. You can pause here. When you're done, press continue. First, let's finish the table here. If both your explanatory variable and response variable are categorical variables, the chi-square test can be used. Moreover, when both the categorical variables only have two categories, the Fisher's exact test can also be used. For the scenarios where the explanatory variable is categorical with two levels and the response variable is numerical, the two-sample t-test can be used. However, if the explanatory variable is categorical with more than two categories, we can use ANOVA. And finally, if both explanatory variable and the response variables are numerical, we can use correlation or regression. Now let's move to the three scenarios below. So if we want to know whether the mean of a continuous variable is equal to a constant or known value, we can use the one-sample t-test. And if we want to know whether there has been a change between two measurements taken on the same person, we can use the paired t-test. And finally, if we want to compare a measurement from one person or an individual to a population distribution of measurements, we can use the z-score method. So here is the end of the course review. The content in this slide is the most important message of the class. Please make sure you understand it, and also in the real world scenario, you need to know how to pick the correct test. Here are the details of the final exam. The access to the quiz will be available for 24 hours on April 18th. The quiz will include 15 multiple choice questions, and you will have 90 minutes to complete the exam. Only one attempt is allowed for each of you, and there will be no makeup test. So please make sure you finish the quiz on April 18th. All the questions will focus on choosing the correct test. So basically very similar to our review practice in previous slides. You will be given different scenarios. For each scenario, you will need to choose the correct hypothesis test to perform. To prepare for the exam, make sure you understand everything in the summary slides I just showed you. Here comes the end of this term's lecture. Take care and wish you all great luck with the final exam.